All right, so not too many more videos left here in Unit 2, Dynamics, right, in AP Physics 1. In this video, we're going to focus on incline planes. The way you think about incline planes, they are just simply ramps, okay? So an object on a tilted surface will often slide down the surface, or as you can see in these pictures, it's going up the surface, but that's because we have added applied forces. The tilted surface is what we call an inclined plane, right? Again, we described this as ramps. At minimum, there's going to be two objects or two forces acting on the object. One is going to be the weight acting straight down on the object, and the other will be the normal force, which is perpendicular to the surface. Remember, normal force mathematically means perpendicular, okay? So basically, if I had a flat surface with a nail sticking out of it, and on that nail I had a string, as I raise this surface, you would see that the nail stays in place, right? But the string, I'm going to put a little washer on it to add some weight, right? The washer, the string would kind of stay in alignment with how gravity would be, okay? Now, if there's more forces acting on the object, you just simply put them on your free body diagram and then solve for what you're looking for. Okay, so remember, at minimum, there's going to be two, the normal force and the weight. In these pictures that you see off to the side here, there's multiple forces, right? So here are my two minimum forces, my normal force and then my weight on the piano. But then, of course, I've got his pull force, right? And then I've got these guys pull or push force. Okay, I may have friction down here. Okay, so this is friction. I've got F pull 1, F pull 2. Okay, so same thing here, right? I've got my two minimum forces, Fn and Fg, but then I've got this pushing force, and then I may have friction down here at the bottom. Okay, now, one thing you have to know is that the coordinate system needs to follow the surface. So if the surface is tilted, our coordinate system, our positive direction, or positive directions will follow that surface, okay? So what that does is really just puts one force in multiple directions, and that's going to be our weight. So what we have to do is we would have to break up our weight component. Sorry, we'll have to break up our weight pieces, okay, into vectors or into components, okay? But what happens is the sine and cosine flip-flop because the angle that we know is actually the vertical angle, not the horizontal angle. All right, so let's look at a couple of example problems here. So you got a 2 kilogram box on a surface that's inclined 27 degrees with the horizontal. The surface of the inclined plane is assumed to be frictionless. What is the acceleration of the box down the incline? Okay, so here's an example where we only have the two forces acting. Okay, no friction, so we don't have to put it on it. We're just letting this slide down, so we have no applied force. So here's our forces here's our weight force that we have to break apart, right? So there's FGY, and here's FGX. But something you see from the diagram, the only force that is causing the acceleration would be FGX. Okay, so there's our draw step. Now we do our sum step, right? So draw, sum, right? And so I'm going to sum in both directions. So sum of the forces in the y direction is going to be equal to 0, right? We're not accelerating through the plane. And so it's going to be Fn equals FGY, which equals mg cosine theta. Okay, this we didn't really need for the problem, but in the event that we do have friction, okay, we would need the normal force. So now let's look at what happens in the x direction. So the only force I have in the x direction is FGX, and that's going to equal to m times a because we're looking for the acceleration. And so I'm going to substitute in my FGX equation, which was mg sine theta, and it's going to equal to max. But note, same block, right? And so it's going to be A equals G sine theta. Now, you may want to write that down somewhere or highlight it because that's a very important equation because this is the acceleration down an incline absent of friction, okay? So now all I got to do is plug in my number. So notice that it doesn't depend on the mass, right? It doesn't depend on the normal force. The only thing it depends on is G, which is constant, and the angle. So we're going to do, let's whatever my notes. So 9.81 times sine of 27. And that's going to give us an acceleration of 4.45 meters per second squared. Okay, so that is the acceleration without friction. The next question talks about what happens when there's friction. Okay, so our free body diagram is going to change a little bit. We got our two standards, but now we have this friction opposing our motion. And so before we talked about our coordinate system, right, tilt it. So if this is a standard coordinate system, we're going to tilt it, right, with our positive direction pointing in the direction that we think it's going to travel. And in this case, it's going to travel down the incline. So our positive direction is going to be down the incline. Okay, so again, here's, I forgot the label. So Fn, Fg, right? This is going to travel down the incline, all right? So what happens is our y direction is going to end up being the same as the previous example. So we get Fn minus Fgy equals 0, which tells me Fn equals Fgy, which Fn is going to be mg cosine theta. All right, now on the x direction, it's going to be a little bit different because now we have friction involved, right? And so we're going to get Fgx minus F, right, which is our frictional force, equals max. And so it's going to be mg sine theta minus mu Fn. That was our formula for friction. And then we're going to substitute in. We have a Fn, which came from our y direction. So we're going to mg sine theta minus mu mg cosine theta equals m times ax. M's cancel because it's the same object. And so we get an acceleration of g sine theta minus mu g cosine theta. So if you look at that first half of the equation, it's basically what we ended up with in the previous question. Okay, if there's no friction, mu, right, frictionless surface, mu is 0. So that whole term would go away, and that's how you end up with that A equals G sine theta. So I'm right over here. So AX equals G sine theta minus mu G cosine theta. All right, and something you would see, our acceleration should be less than our previous answer because we've got the minus mu G cosine theta because we got friction slowing it down. All right, and so we're going to do 9.81 sine 27 minus 0.458 times 9.81 times cosine of 27. Sorry, 7 looks like a backward C. And so we're going to find that our acceleration is going to be 0.450 meters per second squared. So you can definitely see the friction slowed it down considerably. Okay, so that is inclined planes. All right. Now remember, these can be combined all over this unit. Right. It could be in the connected objects section. It could be here with friction, without friction. So just be aware that this inclined planes show up in multiple sections of this unit. So the only thing left is now we combine it with our unit 1 topic, right, of kinematics.